In example number 8, we're going to solve the following system, which is a dependent system of linear equations using matrices. The first equation is negative x minus 2y plus z equals negative 1. The second equation is 2x plus 3y equals 2. And the third is y minus 2z equals 0. So the first thing I want to do is write the augmented matrix. So the first column is the coefficients of the x terms, which is negative 1, 2, and 0. The second column are the coefficients of the y terms, which is negative 2, 3, 1. And the third column represents the coefficients of the z terms, which is 1, 0, negative 2. Then we have our line for the equal sign, and then the constants, which is negative 1, 2, and 0. Now the first thing we want to do is we want to make sure that 1 in the upper left-hand corner is a positive 1, and currently it's negative. So we want to multiply row 1 by negative 1 to get that positive 1 in row 1, column 1. And then we're going to perform row operations to obtain row echelon form. So going from 3 to 4, if we multiply everything in row 1 by negative 1, we get negative times a negative 1 is positive 1, negative times a negative 2 is positive 2, negative times positive 1 is negative 1, and a negative 1 times a negative 1 is a positive 1. And then what we want to do is, we can see here that we want to get a 0 below this 1. So what we can do is we can interchange both row 2 and row 3 in order to get that 0 below the 1. So we're going to interchange both rows for row 2 and row 3. So now we have 0, 1, negative 2, 0 for row 2, 2, 3, 0, 2 for row 3. Now that we have a 1 and then a 0 here, we want to get a 0 here. In order to get a 0 here, we're going to multiply this 1 by the opposite of positive 2, which is negative 2. So here's our rule in step number 5. We're going to take negative 2, multiply it by 1, which is negative 2, plus 2 gives you 0. Negative 2 times positive 2 is negative 4, plus 3 gives you negative 1. Negative 2 times negative 1 is positive 2, plus 0 gives you positive 2. Negative 2 times positive 1 is negative 2, plus 2 gives you 0. Okay, so now that we have a 1, a 0, and 0 here, then we have a 1 here. Now our goal is to get a 0 here and then a 1 here. Now, in order to get the 0 here, we can see that we just need to add row 2 with row 3. So let's go ahead and add row 2 and row 3 to see what row 3 looks like. Well, 0 plus 0 gives you 0. 1 plus negative 1 is 0. Negative 2 plus 2 is 0. And 0 plus 0 is 0. So what you notice here is we're going to write down the matrix that represents this following system from here. So we have x plus 2y minus z equals 1. Our second equation is y minus 2z equals 0. And then our last row, we have 0 equals 0. And this is the dependent system. So because we get a row with all zeros, and this is a true statement, then therefore we're going to have infinite solutions. So in step 8, we see that by the identity 0 equals 0, that this is a dependent system with an infinite number of solutions. And now we can find the generic solution. So by solving the second equation for y, and then substituting it into the first equation, we can solve for z in terms of x. So over here in step number 9, we're going to look at this second equation, and we have y minus 2z equals 0. So what we're doing is we're going to go ahead and solve for y, so y is going to equal 2z. Now what we're going to do is whatever we found for y, we're going to substitute it into the first equation that we have, which is what we have in step 10. So we're going to substitute y to be 2z, and then we're going to solve for z. So we have x plus 2 times 2z minus z equals 1. 2 times 2z is 4z. If we combine 4z minus z, which gives us plus 3z. And again, we want to make sure we're solving for z. So we're going to subtract x to both sides and then divide by 3. So now we know that z is going to equal 1 minus x over 3. And now we want to write y in terms of x. So in order to do that, we're going to go ahead and use the same equation that we have over here, y is equal to 2z, and plug in what we got for z here. So we're going to get y, which is equal to 2 times 1 minus x over 3. Distributing the 2 gives us 2 minus 2x over 3. So the generic solution of the dependent system is that we have x, because this is in terms of x, as our first coordinate. Our second coordinate is is y, and y was equal to 2 minus 2x over 3. And then the third coordinate, which is z, was 1 minus x over